Just for a moment, I want to introduce myself. I'm Terry Vinus. I work for Stowe. I'm the technical services manager there, and I am now the committee chair for our technical and research steering committee for EIMA. We've got a lot of good participants and people that have worked on this committee over the years, have really helped this industry grow and overcome a lot of major obstacles. So I'd like to introduce the folks that are here that are part of our committee. We've got, let's see, I don't think Tina is in here, but Tina Kennedy with Parex. Y'all give her a hand when she walks through the door. Perfect timing. Bill Preston would drive it. Got Peter Harrison with Parex. Not with us today. We've got Bill Egan and Eric Allman with BASF Wall Systems. So we also get a lot of support and a lot of participation from Dave Johnston. And as you'll see from, and we also have Dustin Nathanello, who is new to us, and therefore I'm sorry I didn't remind you. And in all things fire and destruction, we have Jess Beitel, who's going to speak to us in just a moment. So we've had a good year from a technical committee standpoint. We've got a lot of accomplishments. In order to save time this morning and give Jess an opportunity to give his presentation, we are going to just post those in the form of an update on the website. So we'll compose that and we'll get it out that way, and that way you guys will be able to go through the list. If you've ever got any technical questions or things like that, I'm sure you can reach out to any of us that are on the committee, or either through Dave or through individually. So thank you all for being here this morning, and we hope that we're going to make it worth your while to come down here and get started early. So with that, I'm going to introduce Jess Beitel. He's a senior scientist and principal at Jensen Hughes. He is one of the kind of the fathers of the fire technology side of things for EIFS as far as test procedures. But since I haven't studied his resumes too carefully, I'll just let Jess take over. So, Jess Beitel.
Thank you. Good morning, folks. Before I get into the presentation, just a couple points. 2 weeks ago now, one loses time, we went through a week of building code hearings, and I even forgot where the hell we were nowadays. Louisville. Well, you go into this brain dead mode when you go in there for 9 days from 8 in the morning till 11 at night. You're just clueless. But anyway, bottom line is that going through the code changes for the International Fire Code and the International Residential Code, the issues that EIMA had the most concerns about were all defeated, and so those things are now sort of off the plate until we see what happens come October. So some issues, one of the biggest issues is there was a proposal put in from a fire marshal in Florida who wanted to always have gypsum wallboard on the exterior of any foam plastic on the exterior of a wall system, which would have eliminated EIFS. So, but other industries also participated in addressing that issue, and that was voted down. So we'll see if it comes back or not. So anyway, just to give you a heads up that the work was there, Dave was there, Justin was there. Yeah, we were there. All right. So what I'd like to do is give you all a discussion today about water-resistive barriers and the requirements in the IBC for what they have to meet with respect to flammability. Let's see. So I'm going to just give you a quick rundown of some of the history how we got to where we are. Originally, many of you all know, and some of you younger guys don't, that basically this all started in the 70s. All right, first energy crisis way back when. Two industries, EIFS and the metal panel industry, wanted to start putting foam plastic on exterior walls to increase the energy conservation for buildings. The problem was, coming out of the late 70s, there was a Federal Trade Commission consent agreement with the foam plastics industry over the flammability of the foams. And so initially this was not, the code officials were not buying into the concept at all. We had to develop tests and to be able to show the code officials that for the walls that we wanted to install the foam on, which is types 1 through 4 construction, code requires non-combustible wall assemblies, that you could do it. And to do that, we had to develop a test. And so what you see today in the code, NFPA 285, is a test that came out of a generation of tests to look at this issue. All right, the precursor was actually, the original test was an actual 2-story building built down there in San Antonio. Walls installed on it, ran the tests, and showed that, at least for EIFS, for metal panels, they could pass the test. Other assemblies didn't necessarily pass the test. We shrunk it and became 285, and that's what's in the code now. All right, so 285 was originally put into the code to evaluate foam plastics. That's where the genesis of it came from. It went into the codes in one form or fashion in the late 80s. So I always like architects when they tell me this is a new requirement. And it's like, have you ever read a code from whenever? Yeah, and even though we started it for foam plastics, it wound up getting used by the combustible veneer people. The first ones really were the ACMs, the aluminum composite materials, the aluminum faced solid plastic core type veneers. Those were the next exterior veneer systems, and the code would not allow them to be used over 40 feet. So there was no way they were going to be able to put it on a tall building. But turning around and using NFPA 285 to evaluate those veneers, they were able to do that. So in 2000, actually, when we brought all 3 legacy codes together under the ICC, that code change, that chapter 1407, I think, was inserted into the new ICC codes, and so ACMs and MCMs could then meet 285 and be used on any height wall. Same thing happened then, followed shortly by other combustible veneers, high pressure laminates, and EIFS. And while EIFS was still regulated under foam plastics, in reality what the industry wanted to do was have their own section at the end of the day. So the technical committee really worked hard to get through ASTM, several standards which could then be referenced by the code, which embodied then the requirements for EIFS to include the fire testing that's required. And so then in 2009, we were able to insert section, 1408, into the code, which references EIFS specifically. All right. Fiber reinforced plastics, same time frame. You see some of that now being used on exterior buildings. All right, so water resistive barriers. So here we had foam plastics, we had insulation materials, and we had veneers. Turns out water resistive barriers were looked at, and in 2012 a section was added for water resistive barriers. And I'll get to that specifically in a minute. I mean, at the end of the day, what we've been doing since the late 80s is we keep adding combustible materials to walls that are supposed to be non-combustible. All right, that's sort of like not what you really would like to do, but that's what we are doing. And so to make sure that you're doing it in an appropriate manner, I think that's where tests like NFPA 285 come into play. All right, so a couple of things about 285. You have to test an entire assembly. You just don't put a product up there and do that. You're actually testing a true wall assembly. You also have to do Since it's a test of an assembly, if you're familiar with ASTM 119 fire resistance rated construction, you can't mix and match. You maybe, but maybe not. And that's one problem with this. All right. And again, you can do some mixing and matching, but you have to be within very limited limits. If I have an assembly that's been tested in 285 and I want to substitute another material, may or may not work. Definitely, if you substitute one foam for another, it sure necessarily ain't going to work. When you start adding more combustibles, you need to retest in most cases. So for example, many of the tests that was done back early on for people like the ACM manufacturers, they found that they just tested their product over gyp sheathing. Well, that was good back in 1990. In today's world, you're going to have to put a WRB over that sheathing, and now those tests that they did are no longer necessarily valid because you've added new combustibles. We found changes in configurations, again, not for EIFS, but for other types of products. We have actually seen that for some products, bigger air gaps behind the veneer is worst case, but we've also seen in one veneer, smaller gap is the worst case. Who would have thought until you do the test? So this is the problem that we sort of have somewhat, is that you can build a wall with all these various components. I got different interior membranes. I can have different insulations in the stud cavities. I may put sheathing up to meet new energy code requirements. I may put WRBs up. I may put more foam plastic out there for continuous insulation. Air gaps may or may not be there. And you got veneers that may be non-combustible or are combustible. So all of these types of components get varied in these 285 tests. And so you have to be careful when you're looking at a 285. Somebody comes to you and says, I want you to put your water resistant barrier in this 285 test. It's like, whoa, I'm not sure we can do that or not. All right, so let's talk WRBs specifically. WRBs, and we call them, I think, weather-resistive barriers at one point, which was basically felt paper in the codes from way back when in the legacy codes. Over time, and at the same point in time, they were and up until 2012, there was no specification for any flammability testing of weather barriers, water-resistant barriers, as we now call them. As I say, we now call them water-resistive barriers, but they include air barriers, vapor barriers, whatever. More than I want to know. I just deal with the fire. I don't deal with the water and vapor. I don't go there. All right. And so typically over time, these the use of them, which started in Canada, and as it moved down into the States, the easiest way for people to address this issue was, well, we have water-resistant barriers on the roofs. So let's just move them from the roof to the wall. All right? Well, sounds like a great idea. So, except that we have a few problems with that. One is some of these WRBs are very combustible. And that was one of the big issues that drove this requirement in the codes. An example is, this is an NFPA 285 test up near, and looking at the top of the wall system, which is about, this is brick veneer. And what happened was we had a wall system which had interior gyp, steel studs, sheathing, gyp sheathing, foam insulation, foam plastic insulation, and a brick veneer, air gap of about 2 inches. That system had passed the test. All right, but you had to be careful with respect to the window header treatment, because the type of foam we were using, which was a polystyrene type foam, melts and comes down onto that thing, and you got to contain it. You can't let it go. So then they decided we're going to repeat the exact same test, except we're going to put a peel and stick between the foam and the gyp sheathing. And so that's what you got next. That's at about 18 minutes into a 30-minute test. All of that asphalt started flowing, burning, went right up the wall system, which is like, holy cow. So that's a couple of those types of tests are what drove the requirements for putting it into the code to take a look at it, at water-resistant barriers. It requires some type of testing. All right, so currently in the 2012 code, the basic requirement went in which said that if you're in types 1 through 4, non-combustible construction, and you want to install a combustible water barrier over 40 feet, you have to meet 285. It's the same thing that we've allowed for basically combustible veneers. Combustible veneers are always allowed up to 40 feet. After that, they were not allowed. But most of them can get through. If you can meet 285, you can do it. Same thing with the water-resistant barrier.
Why was it 40 feet?
I'm old, but I'm not that old. Okay. Basically, part of that, my understanding, because I've asked that same question of the old timers, is part of that is they felt that 40 feet, the fire department could get it with hose streams back then, do whatever, but if it went higher than that, they were going to have problems with getting people out of buildings and whatever. So they were willing to allow, basically it was for wood, to allow wood sidings up to 40 feet. So that's why. All right. And as some of this code stuff goes, it was like they picked a number. All right. So it's right about 3 stories. So they figured, okay, we can do 3 stories. All right. So 2012 had the basic requirement. You got to do 285. Then in 2015, since we had some experience under our belts, we allowed a couple of exceptions. The first exception is that if the WRB is the only combustible component in the wall assembly, it can be covered with what we call heavy veneers, brick, concrete, stone, those types of veneers, and not have to do a 285 test, because typically that would give enough protection to that WRB from both this exterior fire, interior fire that we have in 285, and be all right. So that was the first exception. The key is it's the only combustible. The second exception said that, again, you don't have to do a 285 if your water-resistant barrier, again, is the only combustible component, and if it meets some fire tests. One of the fire tests is ASTM E1354. It's nicknamed the cone calorimeter. It's a small-scale test. It uses a sample 4 inch by 4 inches. I'll show you a picture of it in a minute. We burn the samples and we get a whole bunch of parameters, which are very useful, and we'll go over that too. But basically, the code said that if it has a peak heat release rate of 150, and then a total heat release and an effective heat of combustion below those values, and you've tested it in ASTM E84 and you get a Class A flame spread rating, you can put it into a wall where it is the only combustible and not have to meet NFPA 285. All right? From what we've seen, the hardest part of that to pass is the peak heat release rate. All right? Yeah, I won't say how ugly it was to get to the numbers, but bottom line is that typically is a number which keeps some of the WRBs out of play here. So this is a cone calorimeter. It's a little small scale type test. Like I say, the sample's horizontal. It's called a cone because right above the sample, where you see the flames, there's a little heater which radiates heat down, but the top's chopped off. So all the smoke goes up through there. Smoke goes up into a hood system, and because we know with the way the apparatus is set up, we measure oxygen in the exhaust gases along with CO, CO2, and the flows of the exhaust gases through the ductwork. Way back when, it was found that in general there's a principle that for most organic compounds, that for every gram of oxygen consumed in the combustion process, you get 13.1 joules of heat energy released. So if you use that principle, and if you know how much oxygen is used in the combustion process, you can sort of figure out how much heat's given off by this sample. The beauty of the cone is that I'll show you in a second, we get a time release of heat energy output, whereas most of the people are familiar with NFPA 259 potential heat that's required in the code for foam plastics. Those types of, for what we call heated combustion, general chemistry, heated combustion of a material that's how much heat's given off by a material when it's burned in an oxygen atmosphere, and you squeeze every bit of heat energy out of it. That's what you get for heat energy. So it's a BTUs per pound type thing, but you don't know how it comes off. Does it come off very fast? Does it come off slow? We don't know. So that's where the cone comes in. ASTME 84, the standard type test, which is run basically, you all run them on base coats, finish coats, requirements. The foam plastics guys have to do that too. All right, so we had two exceptions. One is if you put enough heavy duty stuff in front of it, you're okay. The second is if the WRB can meet certain requirements, you're okay. And then the third exception was put in for our friends in the fenestration industry, which said, if we're putting stuff around the windows and the doors and it's trying to seal whatever, we don't want to have to test NFPA 285 for those types of products and those limited applications. And from all the testing that everybody's seen with respect to 285, while we have a window in there and people do stuff, special flashing and whatever around that window, we've never seen that that's caused the problem with respect to pass or fail. So we didn't have a problem, so nobody had a problem with this. But at least it specifically calls out that if you're going to use some type of butyl flashing tape or a water-resistant barrier around the openings in that, you don't have to meet 285. All right.
So what the peeling stick be, the cone method then?
Yeah, peeling sticks can be used there. Usually within about 18 inches or so. That's fine. Just don't go start moving that peeling stick and say, okay, we're at the window, but by the way, we're going to move it up 10 feet. Okay. So, but anything like a foot, 18 inches around the openings and that is not enough to affect the performance in the test. All right. Okay, so the biggest question is, or the biggest issue still remains, is if the WRB is used in conjunction with another combustible material in that wall assembly, you still have to test because that other combustible will drive the requirement for the test. So even if your WRB met exception number 2, had low flammability performance, that all looked good. If somebody's going to put like an ACM panel up, it's got to be included in the test over the top of it because the ACM is required to do that if it's going over 40 feet. So, all right. Get this question all the time is, I make a WRB. How do I qualify it? Well, it's not a simple process. And there is no one test that we can do which says, you're good to, you do this test, you get these numbers, you're good to go forever, no matter where you go. It doesn't happen. All right. One way that a WRB manufacturers have done this is that they've gone out and actually run an NFPA 285 with one of their WRBs. And typically, if they have a range of WRBs, we'll select the worst one and test that and see how it performs. And then we can get them a limited engineering judgment based off of that. The other way to do this is to get the cone values on your WRBs, and based off those values, we may be able to insert that WRB into NFPA 285 tests that other manufacturers have run. So for example, on WRB manufacturer, I go out, I test my foam, or test my WRB in the cone, my numbers come back, they're nice. And then if I was to go to, I'll pick on, who do I want to pick on? Dow today, okay? Dow has listings or in testing in 285 assemblies where they have a list of WRBs that can be used in their assemblies. And so that is based off some baseline that Dow has done a test on. If your WRB is less than that baseline, we can add you into that list for Dow. So that's sort of, that's a little easier than having to totally run a 285 test. So what we're going to do is you have a WRBX is done in, you evaluate it in the cone calorimeter, so you get your basic properties. You're going to turn around and have that either, typically some of the WRB manufacturer may run a full-scale 285 test with that WRB in there, and it passes. So that's a baseline for him. For that assembly, or that type of assembly, here's the baseline for a foam, for a WRB. And any of his other WRBs that he may make that have better cone performance would be engineered into that, into their systems. This is what the output of a cone test looks like. You see ignition at the bottom left. This is for a fluid applied WRB. You see how much heat is given off, up to a maximum of about 350, 325 kilowatts per square meter, and then drops off pretty fast. So in about less than a minute, it's over with. All right. This is sort of typical of what you would see with fluid applieds. If you had wraps, Tyvek, Dow, Weathermate, it would be less than 50. Peak would probably be a little less too. And if you go with peeling sticks and that, your peaks will probably be higher and it will be extended much longer. So it just depends. All right. And as I tell WRB manufacturers of WRB is, I know you like to sell product, but this isn't barbecue, so don't slop the stuff on there, because the more you put on there, the more it's going to burn. All right, so keep that in mind. Yeah, it's like, how much do you really want? Yeah, I want to put 50 mils. Oh, most people put 20. Well, yeah, but yeah. And then you do the test and you realize 50 mils ain't going to hack it. You're going to go back to 10. So. Yeah. So bottom line is, so here's what E154, out of that plot that you just saw, we get a whole bunch of data. We know when it ignited, how long it burned, what was the peak, what was the time to the peak, average heat release rates over specific time frames from ignition out. We also, because we measure weight loss, we can get what we call effective heat of combustion, which is different than the normal heat of combustion, but it's because we only did it on one face of this sample under these conditions. And then the other one that's important for us is the total heat release per unit area. So how much heat's being released per square meter or square foot up there on that wall system. This is the information we get, so that gives us some idea of being able to compare WRBs. The most important ones, needless to say, are the items that involve the heat release rates, the peaks, effective heat of combustion, total heat release rates. When I'm comparing that I don't really care about time to ignition necessarily and some of this other stuff, but those are the values that we really look at. All right, tough to see, but this is an example of a WRB manufacturer's extension of NFPA 285 test results. He went out and he first started out and ran, it's hard to see here, cone tests on 3 different water resistive barriers. So those are his So that's his product line that he's wanting to use. He went out then and ran an NFPA 285 test, which involved foam plastic insulation, in this case polystyrene foam. And he ran it with a brick veneer. So he did that test, and so what we can say is, based off the results of that test, he now comes in with a whole slew of variations that you can do in the test, or in the wall assembly. For example, we tested steel studs and gyp sheathing. You want to use concrete or CMU, sure, go ahead, be my guest. But the water-resistive barriers, when we designed the test, he had 3. We ran the cone tests on them, picked the worst. So he's got that one tested in 285, and so the other 2, which had better performance, are put into the analysis just based off of the small scale tests. So he doesn't have to rerun that test all the time. And then the other limitations are what you would normally find for a 285 test assembly with respect to veneers and other things. So, all right, so 285. We have found that 285 has been a pretty good predictor of performance of exterior walls. And it turns out that EIFS are one of the best ones that we've had to be able to show that. All right? There have been probably more fires. Well, we know that EIFS have been involved in fires, and EIFS has, when properly installed, has performed well in a fire exactly as you would predict per 285. We've also seen a whole bunch of fires, for example, that have occurred in United Arab Emirates, overseas. All right. It turns out that those nice towering fires are exterior veneers which do not meet NFPA 285. The 285 requirement did not enter into that area of the universe until about 2013, 2014. So all those buildings that were put up before that are all based off of E84 tests rather than 285 tests. So I'm just glad I'm not the insurance companies. 285, the big kicker that I see is people have to realize that 285, again, is a test of assembly and has to be used appropriately. You can make changes. We get those requests all the time from architects and GCs and from manufacturers of trying to say, okay, they want to do this in a wall. Sometimes we can say yes, sometimes we have to say no. It just depends. At the bottom line, we have found, and which we never knew going into this thing, when I started working on, in 1980 was when the first 2-story outdoor test was built, and we ran the test series on EIFS and metal panels. We never thought that this is where we would be at the end of the day with all these various other components in there. But we have learned a lot. We've learned that all foam plastics are not the same. Thermoplastics are different than thermosets. And even within a family of thermosets, performance is not the same when you put them up on walls with different types of veneers over the top of them. You get totally different results in some cases. Veneers are not the same. We have seen that even though it may be an ACM panel, for example, I'll pick on them for a minute, depending on air gaps between them, there may be a problem. We've also seen that for high pressure laminates, they're not all the same. I can't take a test of a high pressure laminate, I'll pick on somebody, Trespa, and say, Fundermax, you want to just put Fundermax on that wall, which is another high pressure laminate. No, they're just too different. So that's a problem. And we've also now come to know and love water-resistive barriers are not the same. All right? The thinner they are, the less combustible they are, the better you are. But as you move up into that combustibility range, they can affect the fire performance of the overall test assembly. All right? So, at the end of the day, you don't want your product there. All right? So, So with that, I'll be happy to answer any questions anybody has. So, thank you. Yes, sir.
Have a list of, parts that failed, that are out there that were challenging that. Nobody
talks about failures. So yes, there are, I mean, it depends upon how you say fail. For example, I'll give you an example. Let's say I have a asphalt type peel and stick, which we know is pretty ugly. All right. So we have seen manufacturers or people, veneer manufacturers, for example, say we're going to put 2 inches of mineral wool as the CI over that, and then put our veneer over that and do a 285 test. Well, 2 inches of mineral wool protects that underlying peel and stick. So once they get that test done and they get the peel and stick qualified, you can almost put anything underneath there. All right, but you got to use the mineral wool. I can't use EPS, XPS, any foam plastic. No, ain't going to happen. So, so it depends on how it goes. So you can use, sometimes you can use nasty stuff, but not always. That help. So there's no definite line, demarcation line, which says if you have values over this, you can never be used in a wall. Yes, sir.
When you talk about a full-scale test on the wall assembly, what are actual proportions of the?
Yeah, NFPA 285 actually is a test of a wall assembly which is approximately 18.5 feet tall, 14 to 15 feet wide. And it looks like a small 2-story building. So I have, in the bottom floor, there's a burner which burns inside the burn room. There's a window opening. Flames begin to exit, and at 5 minutes into the test, an exterior burner comes on and adds more flame to the exterior face. So the wall gets attacked from the front face, exterior face, also from the interior side for the 30-minute duration. So, and flames in that can only, we know, when we designed the test, we knew we were dealing with combustible materials. So we said, we're willing to allow some burning, but not a lot. And so the pass-fail criteria for this test basically is flames can't go 10 feet above that window, either on the exterior face or within the cavity spaces. So you control it. We allow some burning, but not a lot.
And the bottom of that wall assembly is what?
Same wall, everything from top to bottom. Typically, we never see problems on the bottom just because the fire is mainly up on the top and flames are going up that way. So you might see burning at sills. You may see
directly below the wall assembly is coming in from the side of the wall assembly.
Yeah. Right.
Thank you.
So you said some of your exceptions was that, if you had certain over the top, so insert right on water. So what if you have your water being and your foam plastics covered up by a non-combustible product? So I'm back to 285.
It depends. Yes. What's your non-combustible product? If you're going to tell me I'm going to put metal, let's just say metal, like Centria, just not an insulated metal panel, just a metal face on it. Yes, you would still have to do that. The foam plastic drives it in that case.
Once you enter that into it, so if you're just doing waterproof by itself, you don't need to, but
if you could meet all the rest, yes, if you could meet those requirements, those are the exceptions, or if you're under 40 feet. But when you do when foam plastics goes into the wall, the requirement for foam is you test any height wall. So even if it's a single-story building and that wall with foam's going to go on, that wall has to have been tested for 285.
So that's steel building as well as wood. Just switch up real quick.
This is all 1 through 4 construction. So typically type 5 construction, which is wood studs, have at it. It's combustible anyway. We don't care. I always say you're designed to burn. The code guys don't like me to say that. But anyway, yeah. I didn't make the rules, y'all did. Yeah. Yes.
Does this same test apply to applied foam moldings that are going over the face at cornice or top of wall application?
It depends on the answer to that is yes and no. All right. One is for EIFS systems, they have requirement. Each of the manufacturers has requirements as to how you're going to do plant-ons or decorative things over there on their EIFS walls, and that has to be followed. The prime example of not following that's the Monte Carlo in Vegas fire. Right. So we have also seen that, for example, for the one of the big things, especially in New York City and a lot of the older cities, the cornices at the top of the townhomes and that have been removed, and they're now, most of them are fiber reinforced plastic up there. You know, you can mold that stuff and it looks really pretty. They have specific requirements for flammability that they also have to meet. So it depends on the product and how much of it's going on that exterior of the wall. That help you? Any other questions?
The questions, I did have a project that we just came up on, and it was, we entered fiber into it, and, you know, it's like, well, here's the, you know, you can make a test, but there's nothing showing, now you've reached the system, facility places all over the freaking wall.
Yeah, I mean, the problem we're having is, it depends on, we have found, one is the architects, once they woke up, hate 285. All right, they despise it because it's not easy to get their hands around. We don't have a good list like a UL fire resistive directory on 285 tests. I'm sorry, they got to do some work. All right, yeah, it breaks my heart. But if you make some phone calls, you can probably figure this out. And if it's really weird, you're going to figure out either you can or you can't. So, engineering judgments are done on these assemblies and things by qualified people. We do them, Jensen Hughes, but there's other engineering firms that'll do them. People who are knowledgeable say, okay, yeah, you can do this. It ain't going to make a damn bit of difference. So that's always an issue, and that we usually see that having come through an engineering judgment. And there's times we get requests for EJs and we go, no. Here's some other alternatives to try to do this. Good luck. So, Peter?
Yeah, from an EIFS point of view, I think we've got two issues with the joints and the fire test. One is, I will tell you, EIFS will pass. That's not our issue. Our issue is we've got years of work and hundreds of thousands of dollars invested in proving by NFPA 285 the EIFS systems perform great. You'd have to do that all over again to show nothing. We already know that our typical joint configuration for EIFS will pass the NFPA 285 test. Passing or failing is not the EIFS industry's issue. It's very much the issue for some other cladding industries. But the burden, the unnecessary burden, it's really a point of objection.
Right. And we've also seen that at the, I'm sorry. I looked at, with EIFS, the worst case is no joints. Because what I do is I get all of that foam to melt down and come into the fire zone and sit there at the window header. And if that header is not done correctly, it'll break apart and open up. And with that that weight of that stuff coming down, that causes a problem. So to me, it's sort of like no joints is a worst case for some wall systems. Anyway, okay, thank you.
All right, if I could get members of the technical and steering committee that are here to come up here and join me for a minute. We've got a presentation for Jess. I'd like to ask Jess to return. Tina, you're part of us. You can't hide. As we said, moving in front of our fancy band. A lot of people have known you a lot longer than I have. But, basically, this is an award in recognition of highly successful career and dedicated service, in part, to the EIFS industry. Mr. Beitel's significant, meaningful contributions to the EIFS industry greatly advanced this innovative system. His major accomplishments include development of fire tests for use on all types of structures, as well as his leadership and guidance in obtaining recognition for EIFS in both the international building and international residential codes. His diplomatic manner and his unimpeachable reputation in fire engineering science profession contributed mightily to this significant accomplishment, and he will always be part of our industry. Jess?
Thank you very much. I really appreciate it. Thank you. Thank you. Thanks to you. Yep.